Okay, thank you all for taking your time to come and listen to me speak. And I would like, firstly, obviously, to thank the GESGB for allowing me to present at this extended lecture series, and also to Stag, who allowed me to prepare this talk, on my work time. And this work is a combination of work I personally did in Malaysia, where I was 12 years based, working with Slumj, so around the whole region, and with a colleague of mine, Sharif Farag, who particularly worked on the Vietnam case study that I'm going to show you. And it's a sort of lessons learned and sort of review of things that have stood out over time. And I hope something you'll take away how complex it is to really try and understand why and how a basement flows. So I'm just going to, it's an extended talk, so I'll try and take it slowly and bring you with me on this journey to understanding, why there's such a success in Bach Ho as a play, as is a basement play, and whether Anding Tengah is worth a revisit, where it had a show, but there was sort of more of an economic downturn rather than anything particularly, but will it be a play, or could it possibly be a play? And so we're going to just sort of explain or discuss what do we really mean by basement. I mean, obviously there's a geological definition, and then there's also an industrial definition that is a little vague. Normally it's something below what we're interested in. I'm going to introduce my, the Malaysia case study that I worked on, the Anding Tengah field, which we can see here on the map with yellow, and here in the Malay Basin. And we're going to look at the Vietnam case study, Bach Ho, in the Bach Ho Field, which is in the Cuu Long Basin over here of Vietnam. And as you can see from this regional map, they are both positioned on the Sunderland Plate. This plate is a complex melange of oceanic crust, continental crust. It is a complex sort of collision of the Guangdong and during the closing of the Tethys Sea ocean. So it's obviously got a mix of basement sediments. And then we have obviously the strike slip influence over here with the 3 pagoda faults. And the overall maximum stress orientation is north-south due to the Himalayas syntaxia. And then we have an overall plate movement to the southeast. So there's a lot going on, north-south stress. These are from the map of Tengga with, based on drilling-induced fractures and earthquake cushions. And then we're going to look at a work done by Sharif Farag, as I said, looking at the Bach Ho particularly, and one how they analysed the fractures and showing you the results with a PLT that was logged, the production data, to give you a feeling of what is necessary to understand a basement. And then we're going to go back to the Malay Basin and compare it with Vietnam to see why we feel that, or why I feel that, Bach Ho is such a success and Tengga may or may not be. And then I'm literally just throwing this in for discussion, which we can do at the end. Could we use basement for CCS storage? I mean, obviously, these two fields are very deep. Is it likely we want to inject CO2 so deep? But not all, basements are as deep as this. Maybe it's a potential avenue for CCS. And that's really a discussion for all of us. So what is the origin of basement? Well, here's just a generic diagram of the, how it originates, what you probably have seen from your basic geological studies. But just to highlight, maybe you've forgotten, we have this orogenic granite basement, which is known as this I-type, igneous type. And then we have this sort of transitional, which is literally a bit of everything, whereas we have, post-orogenic uplift and collapse, and this will have the igneous, the sedimentary, and this alkaline or anorogenic granites. And then over here we have rifting, which produces this A-type, the alkaline, and the mantle, the M-type, with the mid-ocean ridge. And as I've said about the complexity of the Paleozoic tectonics of Southeast Asia, we have continental separation, we have ocean basin closure and terrain accretion. So, all over the basement of the Sunder block, you have a variety of lithologies. But in the two fields we are looking at, we have a granite from the Bach Ho Field, the I-type, and a more of a sedimentary origin. It's metamorphic in the Anding Tengah field. So what is the classification of basement? I mean, again, this is a little basic maybe, but it's one of those subjects sometimes you just totally forget about. It's obviously, this definition is based on its silica content, and in here the volume of minerals. And we can see that we have a variety of lithologies in the granite family. And then when we look at the metamorphic, we really have such a complexity of mineralogy, whether it's foliated or non-foliated, and all these compositions and cleavages and textures will influence the amount of porosity and permeability you will have in your basement. For even though obviously a true fracture basement has no matrix porosity, I'll show you examples of how within the network of fractures, some minerals are prone to fracture more than others. So obviously, how do we know we've got fractures? Well, the most common source of discovering in your field is core. And here is a number of examples to just show you what we have in the open fractures. We have two examples, and one of them here is strata bound. This is very common, especially in the metamorphic basement. Here we have where, if you have a lot of clay, even though it is metamorphic, so if you've got a shale with quartzite, it's still a more brittle nature of a quartzite that will have a greater tendency to fracture rather than a ductile, shale. So we find that the different bedding in a metamorphic rock will be prone to different degrees of fracturing, and they can be strata bound. And then here we have a network of open fractures associated with an unmineralized fault, which also is part of, can be connected to a network of fractures behind this. So these are the open fractures. And then we have cemented fractures, and the cement within the fracture varies field by field. But we have either quartz fillings, we have here pyrite filling, and then here we have in this fracture a clay filling. And this one is one of the most difficult to interpret in terms of the image logs, which we'll talk about later. But a clay-filled fracture will be conductive, and in a resistivity log can be very tricky to determine which is clay-filled or open-filled. So what's one thing to totally take away, if nothing else, in a fracture study in a basement field, is the orientation of your well. I mean, fractures in a vertical well, especially if your fractures are near vertical, you may hardly come across, your density of fractures are going to be minimal, because you've got a vertical well and vertical fractures. You may cross one or two fractures, and this will give you very little feeling to the nature of the fracture in. In addition to this, you may not penetrate through a fractured corridor, and therefore will totally miss, even those minimal fractures that you see. But what you can, so your fracture density is going to be low, and you are going to only see very few. The orientation of these fractures will also be limited as a result. But then here we are taking an example from Algeria, where we have drawn over the faults and the fractures and then superimposed a horizontal well through it. You can now see that, one, you have introduced a data acquisition bias, and so that you will walk away from this well thinking that all your fractures are a northeast southwest, and in actual fact, you're just not crossing the other array of fractures. So when you start looking at rose plots and doing your analysis of the fracture orientations, you realize that you're just not seeing the other fractures. And then when you drill a well in a different orientation, you'll again see, because of the fractures you're going to cross, the most dominant is perpendicular to your fracture trend. And it's very hard to take that out of the rose plot. You can do an equation for density, but it's not, your rose plots generally to show your orientation. And then here we have, in this well, we've gone parallel to the maximum stress in the region, which are these blue arrows. But you can see as we've crossed localized faults, we create localized stress fields, which influence obviously your min-max stress in the area, which influence the stress on the individual fractures. And not only that, we can see here from this, a long section in one of the wadis that we have fracture swarms. And these fracture swarms compartmentalize your reservoir. And so in actual fact, you may find that you have no or little connectivity between the fracture swarms. And trying to locate your fracture swarms is difficult without maybe high resolution seismic or maybe a VSP. Acquisition from a well. Oops, sorry. So this is what I mentioned about the scale and the permeability. I've got a section here which is actually from Anding Tengah, and we have a scale here of 20 kilometers. And here we can see these lines here are the fractures across a plane. And at the other end of the scale, we have an electron microscope through a sketch of a fracture of a granite. And you can see at 20 microns, there is an infinite amount of fractures within the grains. And this is sort of element of fractal, obviously, situation going on with larger to smaller over the same scale. And this is what I was saying about the mineralogy is important as well, because this is, fluorescence micrographs of altered granite. And you can see that we can, in the feldspar, we have I do not know which one of those is probably more or less, but there's obviously different types of porosity within the grains. So, and this is vital to connectivity, because obviously with your fractures, you really need the connectivity, the permeability, because you don't have the assistance of the matrix. So we're going to now look at our case study today, and this is the Anding Tengah, Malaysia. And this is a cross-section through the Cuu Basin, across the Tengga Arch, this is south to north, into the Malay Basin. And below it is the sketch of the section above, and this is from a paper by Madon in 2020. And this line here, which you can clearly see on the seismic, is known as the BTU, the below tertiary unconformity. It's extensive over the Malay Basin and parts of Asia. And it marks this massive hiatus from the Cretaceous to the Eocene. The only sediment after the Cretaceous here is these sort of beige Eocene sediments that are located in this sort of syn rift. And here we have these folded Triassic rocks that form within the unconformity. And these rocks are Jurassic Cretaceous granites and metasediments. And there is some evidence of limestone, which is some pre-tertiary reefs on top of some of these extensional basins. We've got the Malay Basins filled between 1 to 7 kilometers of this sedimentary rock. And and our buried hills in the example we're going to use is about 2,500 meters from the surface. And the source rocks that we see that are in this basin are generally this L layer of shale that sort of drapes the tertiary boundary. And there's potentially some source rocks from the Eocene rocks. Here is a map of some of the sites that the basin, the pre-tertiary, has been drilled. And there's about 70 wells, and maybe a bit more now. And our area that we're looking at is here, Anding Utera 1 was drilled in 2004, adjacent to the Tengga Arch. It's drilled down to 2,610, and it crosses this phyllites and quartzites with strong foliation. But as you can see here, there's been carbonates, siliciclastics, granite. It is a melange of basement, as we've mentioned before, from this aggregation. But the one obviously of interest today is the Anding Tengah here. Here is a sort of example of some of the basement rocks that were seen from the Anding Utera 1, and you know, it really is hard to believe there is any porosity or permeability in them when you look at them like this. But you can see the phyllite and the quartzite. In B, we've got the phyllite schist, so we do have the sort of foliation. And then we have the, you know, here's a cross section of the basalt. You know, they're you know, and with these examples that, you know, it is very difficult to see that there is much porosity permeability, but as you've seen in the pictures, it's not in the matrix, it's in the actual fractures. And what we have drilled in the Anding is a FMI. So the FMI, or resistivity tool, is an image log, and it's sort of 360 coverage. Here we see 0, 360, so it's the north, the middle is south. It is a deviated well, so you have to accept that your you know, if you see any min and maximum stress, it's not totally responsive to the overburden. But here we are seeing green the foliation that we saw from the phyllites. We can see a really strong dip direction of that foliation. Each one of these is 10 degrees, so that's about 40 degrees, 30 to 40 degrees to the northwest, continually through. And where we see our resistive, more resistive beds, some of this is the felsic, sorry, some of the mafic kind of rocks, which are more dense. And here we've picked separately in a different track is the conductive fractures. And these are around 80 to 90 degrees. We have discontinuous fractures that are in the light blue. And we can see a strong north-south orientation to our fracture trend in the Anding. When we look across the field, this is work done by Madon. We can see that the faults and some of the fractures, and so not only do they also see a north-south, they see a strong, you know, east-west and a northeast southwest. So there's a variety of orientations, and again, as I mentioned before, it really just depends on which orientation these wells were drilled. But the north-south trend of our fractures is parallel to the maximum stress that we saw in the first slide. So here is a seismic cross-section close-up of that top of basement, and then we see the source rock up here, this shale. We see that we have this faulted upper surface, you know, with infills the Eocene, some of the sediments, but we see the faulted top, irregular surface of that tertiary basin. And we can see that when we look closer at that image that we saw before, there is a massive conductive open fractures here with quite a, you know, a couple of inches in its aperture, and with a mesh-like network. So we could imagine, even though we saw from the core that it was impossible to penetrate, or at least it looked that way without electron microscope, you can see that the basement is fractured and would potentially flow. So to summarize what we've seen from the Malay Basin, from the Anding Tengah, we do have igneous, but it's we have some maybe dikes, but we see mostly metasediment in Anding Tengah. It's Mesozoic to Paleozoic age. The Horst is approximately 1,000 meters, but it's not only at the margins, obviously, to the basin. It's part of this Cenozoic rifting of the Oligocene to Miocene. That's the age of the basin above. It's northward trending pull apart extensional rift basin along a major northwest-southeast strike slip. And the source rocks are overlying the Eocene and late Oligocene lacustrine shales that you see above that, with the margins, with the relief of the basement, we can still migrate the source rock into the reservoir, and then maximum stress orientation northwest southeast and north-south striking fractures with subordinate east-west. So now we come to look at Bach Ho Field in Vietnam, and here is a cross section of the field in question we're going to talk about. We have about 6 to 8 kilometers of sedimentary rock above this granite Horst. It's pre-tertiary, just like before, but this time it's mostly diorite or granite in its composition. And the shallowest part of it is the hill is about 3,000 meters. So it's that much within the base, within the sediment. And what you can see here is that we've got faults, a multitude of faults terminating on the top of the granite structure. The basin, the Cuu Long Basin, outcrops on shore, and these are a field trip to go and look at the outcrops. This is the area we're looking at, just here with the onshore, and this is sort of reconstruction of the region during the time of deposition. The dominant orientation of the fractures are again north-south with northeast-southwest. And this dark feature coming into the granite is a dike intrusion. And what it's seen from the outcrops is the dikes are not necessarily intensely fractured, but obviously the contact with the granite creates a fracture system. And when you look closely at, although you have a multitude of different fractures in the exposed outcrops, we can see we have many crisscrossing different fracture networks, which is exactly what you want to create a permeability. But when we go closer to looking, we see that we do have cemented fracture sets. We have this clay-filled fracture sets, which obviously are going to impede our flow, and we're really looking for those open fractures. So how do we identify fractures in the subsurface? Well, we've already talked about the fact that we could have core and find our fractures. We probably want it orientated so we can get our fracture orientation. You can pick off core if you do a 360 rotation, but generally it's limited and it's hard work getting core from granite. So some of the key tools that assist in identifying fractures whilst logging, these tools are both now available in wireline and LWD. One is the sonic scanner, and this is an acoustic tool, sonic tool, which measures really anisotropy and the reflection and refraction and attenuation of that sonic curve. But what is key to the sonic tool is it will only see open fractures. It does not reflect off a closed fracture, and therefore this tool complements the image log, which in this case we see a partially filled, partially open fracture, which means that it's conductive, but it's propped open by a mineralization. And so we know that this is available to flow because we've lost, and there's been attenuation of the energy flow through the fracture. And in addition, what we can do with the fracture is we can start to look at the aperture and quantify the width of the aperture. You see here they're conductive, to try and quantify porosity, which in the absence of your matrix, and bearing in mind you are trying to calculate reserve, you need to have some kind of number for a porosity. And here we can determine this from the image logs. So this is just a summary of what of the tools. There are pitfalls, but this is you can either use, if you're using oil-based mud, you'd use an ultrasonic, which is acoustic, so you're not hindered by the oil-based mud. This is a very good tool for seeing fractures, and it can see them open or closed regardless, which is an asset. But we obviously have trouble matching our image to core. The scales are different. We've got, even though it's a high resolution, the image log, we are looking at fractures in the subsurface, whereas a core has already been brought to surface. Finding a absolute one-to-one connection is very hard with core to fractures. Then we have here the sonic scanner, which, as I said, measures the reflection, refraction, and modal conversion of the transmitted acoustic energy. We can get the compressional shear, which is obviously, and the stony waves. The fracture detections depend on the dip angle of the fractures. It's not very good if you start deviating too much, and in the if there is bad borehole, you can it will struggle to acquire data, just like the image log. But what is one measurement that does come out of the sonic tool is this measure of attenuation. And what you can see here, this is the green line, and where we do not acquire a waveform because of attenuation, we clearly see that we have the green curve, which obviously now is showing us exactly where we have a fracture sets. Now we can't get the aperture, we can't get the orientation and dip direction, but we can get that from the image logs. So these two tools are sitting perfectly together. And another tool that and these tools that what I'm explaining, why I'm explaining, is that we will look at the results from Cuu Long, from the Bach Ho Field in Cuu Long Basin, and we will hopefully, based on this background, you'll be able to sort of understand the log data I'm telling you. But what we have here is the different types of dips acquired from the images, with the red being the enhanced apertures from sort of a regressive metamorphic in the granite. We have the continuous conductive fractures and the partial in blue. And we also had the lateral log. And through calibration with the image log, although it doesn't have the same scale, we can see these spikes, conductive spikes on the lateral log. And it will measure an accumulative aperture. And we've been able to calibrate the two to use traditional logs to ascertain where the fractures are. In addition to this, we don't always have to run high end. I mean, once you've established your, confidence in where the fractures are, you can start to look at calipers, where if you have an orientated caliper, you can measure the borehole direction. If we have a washout, it's often due to a fracture corridor. We can also see drops in temperature, where if there's gas, which will drop the temperature. So here is our thermal gradient, where we see our temperature log drop within. Often it can be water or gas, hopefully not water if you're looking for oil. But anyway, they're also indicators of a drop in temperature, increase in fracture zone. And then we have the mud log, which is a great tool for the ROP will rate on penetration on the drill will increase if we're going through a fracture zone. We might have drill bit drops, we might have chatter. we might have gas spikes. So these are all great indicators of fractures. And what we're trying to establish here is a sort of rather to eradicate a false positive. So if we can look at a fracture on your sonic, we can now start to compare all the curves to see if the fracture is now seen on, on the multitude of logs on different measurements to give you a super confidence that you're correct in your analysis. Obviously, if you have a spectrum gamma ray, you can often see the uranium spikes, where often maybe uranium salts are precipitated on the fractures. We can see density measurements decrease over a fracture zone. The PEF could increase, is likely to increase because of the mineralization. And then what we said just about the lateral log is it will start to spike conductively as it measures the mud resistivity, the drilling mud. So here we are finally into the real log data that we acquired in the field in Vietnam. And so now, hopefully, from your quick, swift learning curve on log data, we can see here we have the gamma ray. Now, we have, although we can clearly see we drop the gamma ray as we hit the top of the granite, where we see increases in the gamma ray is sometimes where we have more potassium feldspars because they give off, potassium, obviously, which affects the gamma ray. So we can start to see, bedded units. This is just the deviation, but here we have the calipers, and we can see there is a borehole issue here, which could be due to passing a fracture corridor. However, our deep LLD, deep resistivity does not show any, has a high resistivity, so suggesting that it's the formation and it's not the fracturing. But where we see the yellow is these low conductive spikes, suggesting that we're in a fracture zone. And then when we look at the density neutron, we can actually see that we're again spikes that match the same markers as the LLD. And then here we have that dip data that I said from the aperture. This is 0.1 to 1 micron. And this red curve is the RT aperture, cumulative aperture, which has been derived from the LLD, calibrated to the FMI. And then here we are, is just trying to create a sort of cumulative porosity curve from the apertures so that we can start to look where we'd like to perforate. And here we see again converting that porosity to permeability, and we can start to see, based on our apertures, again where we're likely to create flow. And we've divided the log, the well, into 3 zones: 1, 2, 3, to locate the perforation zones based on the apertures of our fractures. And when we look at the FMI over this section, it looks good. This was how we picked our images. We have loads of conductive fractures. It's massively networked. We think, well, this looks good. I've got a vast network of open fractures. But when you actually look at the core, these fractures are actually clay filled. And again, when we looked at the sonic scanner, these fractures were not evident. So again, this is a warning on to making sure you combine all your tools. Anyway, so now we come to some of the juicy bit, and we're now looking at this is the sonic scanner. We've got this is juicy bit. That's not quite. That's more the PLT, but this is now looking at the results, looking at aperture derived from different tools. And we have here the blue apertures derived from the resistivity tool. We have a sort of porosity, sorry, from the Stoneleigh, from the dipole sonic, and this is from the image tool. And this flag here, this bar here, is where we have all. So this is to eradicate, like say, false positive. We want to see the same fracture response on every log. So that here we have, where you follow my cursor, we start to see a spike on all the different tools, and we have multiple flags. We can feel confident that this is real. And it's a process of elimination. So if you see it just on the image log and nothing else, it's just it's just noise. So when we start to look at, this is the PLT. So from this well, here we have the image aperture, and we have the permeability, and we start here to see this is the oil kicks, and here we have this blue here is the holdup for the water-based mud. What we see clearly, we have a temperature drop, start of the production of the oil. We've got the image here where we see a conductive fracture a little bit lower, so this 10, 20, 30, 40, nearly 50 degrees going to the southwest. From this initial lower fracture, we see 50% of the flow. And as the second zone, that zone 3, zone 2, we saw 20% of the flow from what we'd what we'd predicted. And then we had 30% of the flow from zone 3, which we had predicted that it would be much more productive based on the aperture size. And in fact, our fractures were propped open here with mineralization. Here the dips are higher, and it's possible that this super high angle prevents it from crossing other fracture zones. So just to sort of reiterate what I've just said, we thought we had it nailed. We got a very nice workflow to be sure we've got real fractures, real open fractures. Yes, we did nail the perforation zones, but there is no doubt that we didn't foresee that the upper part, that this lower part was going to be the greater producer compared to the upper. And the only possibility with this mineralization within the aperture is that they would possibly, over a long time, this would flow for longer, because they'll be propped open. And this is just just show you that in this type of fracture, these are enhanced by a sort of regressive metamorphism, a sort of dissolution. But maybe that higher angle prevents it being interconnected, regardless to the lower. And just as what comes up a lot, it's not as well publicized, but it's starting to take hold. Is these fractures are propped open by a stress regime, a localized stress regime. And so although you have our regional stresses, which we saw as north-south, a localized fault can cause a sort of contortion of the stress bands, and this allows the fractures. So over here we see that our maximum stress is pushing the fractures closed, but here where we see a sort of strike slip or a shearing on the margins of the same fault, we're holding our fractures open. So one possibility is that basal fracture is propped open due to a stress state. Another thought is that our large fracture in the upper part of the borehole is high angle and not connected. Whereas our lower down, where our first fracture set, although there was small aperture, the lower angle allowed them to connect into a higher connectivity of fractures that allowed it to flow more. So to summarize, we've got our basement type, granite to granodiorite. We've got it Jurassic to late Cretaceous. We've got a buried hill. We've got the same kind of overbearing sediments, the Legacy to Miocene, pull apart, strike, slip. We've got the same source rock, lacustrine shales overlying. The maximum stress is very similar, and the dominance fracture stress. The only thing partially which is possible is that we have a stress state of our fractures for normal strike slip faulting. The fact is, I actually do not know if the Malay Basin is under a stress state for some of those lower fractures. But just to sort of compare what we've just discussed, what is clear on from the basement high in Malaysia is, we had abundant fractures. We could see that. We did not know if they were open because the sonic actually didn't work too well in the borehole conditions and the deviation to concur if they were open. At the time, there was oil show. We know that. There's absolutely little from the matrix. And what is potentially possible is we don't necessarily have the relief that we have over here in Vietnam. So what we see here, there is almost 1,000 meters of relief on our basement, and this Bach Ho the high is surrounded by the source rock, allowing a lot of seepage into the side. In addition, our faults appear to terminate on the tip of the structure, obviously with the seal on top allows a containment of the oil. Whereas when we looked at the cross-section here, we actually saw some of the faults and fractures penetrate through the tertiary, pre-tertiary into the tertiary, which is possible in leakage pathways. But, but maybe, where a better target would be is to look for higher relief features to allow for this. If these Eocene sediments got source rock material, there may be a potential that it would infill the basin. So just to compare the two, we've got obviously I types and S types. Okay, there is more complexity here. The meta sediments may cause a barrier to flow of course it would do, because stratum fracturation in the quartzite compared to the shell will obviously prevent total connectivity, whereas in a granite we may not have that limitation. We're both buried hills, we've got similar types of basin, we've got the same source rock. There is the diagenesis. There was, the weather top of the tour actually produced no flow type, but there was hydrothermal enhanced fracture porosity in the Vietnam. But there's not to say that's not the case in Malaysia either. And they're both more or less stable-ish tectonic activity, although it has been analysed that there is stress fractures in Vietnam. So just to show the schematics of the two, on paper they sort of look very, very similar, except for the source rock, and that for me is probably the issue. The source rock is above the basement, whereas with this strike slip move and reverse faulting that happened in Bach Ho, we've increased the relief and allowing for the source rock to enter into the system. And because it's produced at such a vast amount and for so long, it's the recharging is continual. So recommendations, obviously identify the basement rock type. The metamorphic sediments are going to be much more complicated in the fracture network. Our faults and obviously our shear deformation are going to enhance the fracturation. So it's good to go head towards a fault. We want to look for conjugated fracture sets if possible, because we've got to increase the network. That's vital. If we have, late stage diagenesis or metamorphic regression, that's obviously going to enhance the apertures. Paleoweathering, that may be important for some. Certainly in Yemen, the top of the granite is almost like a sand. So it's not really even a granite, right? It's just weathered granite into a sandstone. And then, is the key the stress fractures? If to keep them open, it could be these going back to a localized faulting system, possibly can prop, and why some fractures are open and some are closed, or some flow and some don't, is because their association with a stress regime. The complex relation with the source rock. There needs to be enough relief of the basement to allow migration into it. And then, can basement rocks be a candidate for CCS? Well, I'm just going to discuss this on the next slide, the nearly last one. And then just quick on the logging. I can't help myself, ex-Schlumberger and all that. But, obviously high resolution 3D seismic. Geochemical logging can really help to do the mineralization, to understand whether you've got a granite diorite, a basalt, a dike. Obviously, the images in the sonic log were super complementary. But obviously the calipers, the resistivity, the getting the aperture from the micro induction log, was certainly in a collective aperture, was ample. High angle wells, you need to cross as many fractures as possible. And the well trajectory aimed at maximizing fracture density, bearing in mind that once you go diagonal, you're going to bias your data set. So not relying too heavily on the Rose diagram, the orientation of the fractures, because that will be totally biased by your trajectory. So just bear that in mind when you think you've got a dominant north-south trend, but actually you've just been drilling east-west. And then just a thought, nothing to, just for discussion. There has been test experiments done into to put CCS, CO2 injection into granite. And this is just a diagram, the phase diagram, to show that, obviously it's normally injected at the supercritical. It's hot, it's fast, it's got a bit of volatility. But the fractures do incorporate the CO2. There is some dissolution which allows it to enhance the fracture networks. Now, of course, the massive issue is the depth, of course, is if they are too deep. But possibly, they may turn out to be a possible injection source, maybe the Lancaster field. Although they're deemed a large porosity, it turns out with all that connectivity, they can have, a wealth of porosity. So anyway, I just want to thank you all for listening. I don't know if I'm over or under. I have no idea of the time. But I'm going to thank Geode-Energy, which was the original company that started on the work. Well, obviously Schlumberger too. And Meaningful Petrophysics, which is Sharif Farag's company, that he did the analysis on the log data, and of course Stack for presenting. Any questions?
I wonder, Melissa, can I ask a question, please?
Yes, sure.
Thanks. Yes. Thank you for a very comprehensive presentation, a lot of thorough work. I just wonder in how much of what you do you come across artificial intelligence. I have many times been encouraged to use AI on seismic data, and I'm very, very cautious about it. And I just wonder whether, with all of the analysis you're doing, gathering, fractured directions and everything else, whether there is something that could be applied in all of the data gathering that you do.
Well, yeah, I mean, it's true. I mean, I always sometimes, I imagine how wonderful it would be if you could just say to AI, right, is there a correlation between fracture density and lithology? And but the truth is, in the oil industry, the different types of data, the PDF, the ASCII files, the TIFF files, the old diagrams, the maps, the seismic. I just think it would take you so long to put this into a form that an AI could understand. You might as well have done it yourself. That I know that's probably old-fashioned thing to say, but it is a vast amount of different data, and the software, each obviously phase of it has a different software, which of course it would be nice not to have that, but your PLTs and the clips, your image logs in TechLog, your IP is your, so they're not seeing each other at all. So I think I always thought that it would be lovely to have that flag, and I did think about it, where because I feel like the mud log, it's often lost later on, in because it's only a PDF. But if you could have a sort of, okay, I saw a fracture here in my mud log, that positive, um well, to prevent the false negative, the I don't even know how to say it, but you know what I mean. So if you see it in FMI and you don't see it in Sonic, to keep that element. So I think I would, yes, I would like to think I don't, ultimately why not? But I think once you've done data preparation, I think everyone's lost the interest in it. I mean, seismic, I don't know. I mean, I did a project on ant tracking, which I suppose is AI in a way, and we just told it, we fed it, the dip data orientation of the fractures, and it followed it. But I could equally have told it the other way with a different set, and it followed that. It follows whatever you tell it.
Well,
So
yeah, I think that's the key. More and more with AI, I believe it has to be educated properly.
yeah,
Tell it what it should be looking for, and then let it go, rather than just let it go.
yeah, 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 yeah. I mean, things may have moved on from back in the day when we did the sound tracking, but like I say, when we told it which way to look, it did look and it found us lovely stuff. But I'm sure if I put the fracture dip the other way, but that's also, like I said, that the fracture thing is a real. When you work on something for so long and then you start thinking, God, I wonder if any of it's right. you know, and and then it was only when I worked in sort of Qatar and they sort of drilled, around, in a 360 pattern. You're like, oh, look, they're perpendiculars everywhere.
Yeah,
And so
well,
what does that
fair
mean?
comment. I'm a little bit worried about my co-pilot because it keeps telling me what I should be doing every day.
Oh yeah. Yeah,
Thank
well,
you.
I
Yeah,
mean, I did do the only thing actually, I mean, I was a bit disappointed in trying to get Copilot to help me, but the only thing it did actually do, which is quite tricky, is I said, please summarize the origin of the Sunder block, because there is thousands of papers. I mean, whether it was right or not is a different thing, right? I just couldn't plow through the papers in time.
yeah,
And I know how controversial that all is, um, because there's so much debate, and Robert Hall was always falling out with other people, because it's so complicated. So I was, there's no way that I could spend too much time on that. But I mean, there is. I think it has to be seen as a starting point. But I found when I googled, tell me about the fractures of basement of Malaysia and Vietnam, it just found me. And I was like, I don't want to. I'm definitely
no,
not the oracle. Can we, So it seemed to source like 5 papers. I I can source 5 papers. I really wanted a deep
mm,
dive
mm.
into a bit more, but I don't know what I'm doing half the time. So I'm sure maybe if you, but but AI, of course, what, like I say, I like the fact it summarized the structural history because I didn't know it. You could
Mm.
say, yeah, I run the AI on your seismic, you know, is it right or wrong? Do we,
Mm.
only you, right? The user can decide that. Um,
Well, I
that's what I
think
feel.
the key message there is that for anybody using AI, you are the one that actually has to make the decision at the end. Don't necessarily believe everything it says.
Yeah.
Mm.
Well, yeah, exactly,
Yeah,
exactly.
yeah.
I mean, but that's the trouble. I'm happy to believe when I don't want to do any more work on it, I mean, that's the and that, you know, we already like we got the calculator and now we can hardly work out anything without a calculator. We get AI, we may not know how to do anything, as humans. And we don't know, do
Well,
we?
I'm glad we're doing this now while we still can.
Yeah,
Mm.
exactly, exactly. And that analytical, yeah, it did look, but yeah, I mean, I've looked at millions of logs, right? I suppose I'm the AI. I mean, that's the thing. But I mean, I suppose it's a great way of passing on information. But I also wonder how it works with, like Google. If you make a company or whatever, it asks you, do you want to promote Google? Do you want to, put it first when it's, do you want to be? So is AI being influenced by who's promoting their stuff? In the end, it is a business too, isn't it? So is it promoting? When it does a search, who's it picking? Um, and it's not analyzing; it's taking a paragraph from a paper
Mm.
and it's putting it on a piece of paper. So far, it's not analysis; it's just a summary of quotes. You know, but I do think for academically, this is brilliant. Because you can't find all those papers quickly, and it is. I've always wondered when we wrote all these papers, they were so lost, weren't they? Is you had to go to the library and you had to get it printed, and
Mm.
you know, so I think it might bring back to life papers.
Yeah.
Yeah, please, yeah, carry on.
Are we the only ones here now? The three of us.
Uh,
Yeah, I just remembered to tell the thing about conference. Let me just say thank you for really interesting and fascinating talk and all that. A lot of it, I, from back in the day, I did some work on Bow High and all that. And I was thinking, I suppose it takes the whole EOR, enhanced oil recovery sort of processing that was going on much further. So it's really quite fascinating to see what can be done with all that data. Yeah.
Yeah, I mean, the only funny bit is really that after all that data, they still didn't know why it flowed. It's just like you were just left with more questions like, yeah, okay. And that is a good thing. You found the perforation zones, right? I mean, that saves the fortune. But the fact that with all that data, it couldn't predict which would flow more, I mean, makes it, does make it so, what is the magic X
Yeah.
factor in a basement that makes it flow? I mean, because there's obviously a field adjacent to Bach Ho that didn't flow at all. I think is it called Dang something I wrote down. Dai Hung, field that they never got it to flow.
Mm.
Same granite, just the same, you know.
Mm. And I suppose the cost would be prohibitive in terms of, how much you can sort of keep going back to, sort of run another sort of suite of logs and, in a different sort of orientation to try and constrain that data. Mm.
Yeah, 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 yeah. I mean, and normally these wells are sort of study wells. I suppose after that, I mean, that is the thing. You've identified how to find the fractures. If you feel afterwards that the caliper is good, I mean, like the caliper, but that resistivity log,
Mhm.
that's good enough. You can run with that afterwards. You don't need to run the high end. But now, in the back in the day, they didn't have sonic and good image logs on LWD, but they do now. So you can be doing this now in LWD,
Mm.
data set. But Yeah. Well, I'm glad you came because I'd have had no one else to speak to. And I've been preparing this for ages. So when it was going to be cancelled, I was like, oh my God, I don't want to prepare it again. We do it in October. So, and we've recorded it anyway. So
Excellent.
I'm going to put it on my YouTube channel. And,
That's been fascinating. Yeah.
yeah. So, well, I'm glad you like it. I don't know if Tamara has anything to say.
Thank you very much. It was a great talk, and I will edit the recording. Do you want me to edit the recording with the discussion, or would you prefer just the talk for your YouTube channel?
Let's keep the discussion. Why not?
Okay.
I did have some followers.
Exactly.
I owe you both a pint.
Drinking on it.
Suffering in the evening on this glorious day as well.
Yeah. All right.
Amazing. Well, thank
Great.
you everyone for joining. And Melissa, thank you very much for the presentation and for your time. We appreciate it, and hopefully we can organize something in the future in London in person.
Yeah,
And
that would be nice.
Diolch yn fawr, Melissa.
Oh, yeah. No, thank you.
Thanks.
Nos da.
That's that, Cariad. Okay, well, thank you, and bye-bye.
thank you very much.
Farewell.
Good night.
Bye.
Thank you.
Bye.
Bye.
I gotta work out how to leave this. I don't know how.
Yeah.
We're all stuck in trying to.
Right, I'll end the meeting.
I got it.
Yeah, because I'm a newbie back to Zoom, so getting